So, welcome students to this second lecture of an interesting topic that we were discussing on biomolecular spectroscopy. So, if you remember last class we started with basic concepts of a spectroscopy. What is spectroscopy? It is a light matter interaction. So, there has to be a light source and that light source should fall to an matter or object, and then whether it is scattered or absorbed or transmitted, the phenomena should be detected by a detector and then process that information and then plotted in some form, that is spectroscopy. So, measuring this light source interaction by some detector and then process that information to understanding the behavior of a molecule, this is studied in biomolecular spectroscopy, right. So, we were discussing that in any molecule there is a energy level, right, that is what we discussed, energy level, and that energy levels are quantized, that is coming from the physics concept. So, there is a ground state where the most of the particle exist, and then there are several excited states, and these energy levels are excited when we do any spectroscopy, right. So, the lowest energy level will be called ground state, and all other energy level we call it excited state. So, this is the first excited state, then we will have second excited state, third excited state, fourth excited state, and if there is more than one levels, energy levels are there, they can be called degenerate state, right. So, in many spectroscopy you find many degenerate state, and that degeneration is not good for a spectroscopy. So, one had to lift that by putting some perturbation, that the interaction or influence of some external stimuli. In NMR spectroscopy we do it to lift that degeneration, we put the molecule in the magnetic field that lifts it. So, in many spectroscopy that degeneration lifting is required, but essentially in a spectroscopy we shine the electromagnetic wave here and that takes the molecule from ground state to excited state, and that is phenomena that we studied, right. So, how these energy states are coming? They are coming because of, if you remember your basic concepts of the molecule, right. So, here is my nuclei. In the nuclei what are there? P plus N. What is proton? So, P is proton and N is neutron. This is positively charged, this is neutral, and around that what we have? Electrons, right. That is in any molecule. So, if you remember, say we are talking about sodium, sodium 1123. What it means? Sodium 11, number of electrons are 11, number of protons are 11, number of neutrons are 12. That is constitute about sodium. So, first discuss about the electron. So, if we discuss electrons, they are distributed, if you remember your 9th class chemistry, in sodium it is a 1s2, 2s2, 2p6, 3s1, right. That is how electrons are distributed in electronic orbital, and then each electron will have two, like a preferred spin, up, down. So, that is the orientation of that. Then in the nucleus, the protons and neutrons, let us call them collectively nucleons. So, in nucleus they are there and they are also distributed in different orbitals, that is a nuclear orbital, this is electronic orbital. So, in nucleus there are nuclear orbitals, they are distributed, and here the electrons are also distributed in electronic orbitals. So, what kind of spins and the orbitals we have? So, first is electronic orbital, then electronic spin, nuclear orbitals and nuclear spins. So, that all we have in any atom, and that is the crux of all spectroscopy that we see here. Interesting part that they are quite independent of each other, electronic spin and nuclear spin, their energy levels are very different. So, they do not too much interfere, there will some influence, but electronic spin and nuclear spin work very differently. So, this is an approximation that we take in spectroscopy in real case, and assume that it does not matter so much that electron to the electron what nucleus do. So, they, although it is in the same atom, these proton and neutron in the nucleus, electron on the outer shell, इलेक्ट्रॉन को कोई फर्क नहीं पड़ता है कि प्रोटॉन और न्यूट्रॉन क्या कर रहे हैं, ये दैट्स द मेजर एजम्पशन. एंड सिमिलरली प्रोटॉन न्यूट्रॉन को इलेक्ट्रॉन के करने से बहुत ज़्यादा फर्क नहीं पड़ता है व्हाट इट इज़ डूइंग. सो दे आर क्वाइट इंडिपेंडेंट ऑफ ईच अदर, राइट. सो इन रियल केस it assumes it does not matter so much the electrons what the nuclei do and vice versa. इलेक्ट्रॉन क्या कर रहे हैं, न्यूक्लियन को फर्क नहीं पड़ रहा है, न्यूक्लियंस क्या करें, इलेक्ट्रॉन को फर्क नहीं पड़ता है. सो देयरफॉर वन कैन कंसीडर दैट न्यूक्लियर स्पिन without taking into account a nuclear vibration and a vice versa, right. Therefore, each subsystem contributes to total energy. So, when we want to understand the energy of any atom, what all energy we have? E electronic, then E vibrational, E rotational, right. E electron spin orientation, then this is all electron, then we come to E nuclear spin orientation and E translations, that is all constitute the energy. Now, therefore, the energy due to orientation of spin of electron, that is called electron spin orientation, and energy due to orientation of spin of nuclei, that is nuclear spin orientation. So, one operates at a nuclear level, this operates at the electron level, and then there is translational movement of this molecule because of thermal energy, that is a E translational. So, that is what I was saying, these all are due to electron, this is due to like a nucleus, and this is because of movement in this space. So, we are going to discuss in detail little later that what I was saying, इलेक्ट्रॉन को फर्क नहीं पड़ता न्यूट्रॉन क्या कर रहा है और न्यूक्लियन को फर्क नहीं पड़ता इलेक्ट्रॉन क्या कर रहा है. दैट इज गिवन इन सम concept called Frank-Condon principle, which is an approximation that electronic transition is most likely occur without change in the position of nucleus in the molecular entity and environment. जब इलेक्ट्रॉन का ट्रांजिशन होगा न्यूक्लियर के मूवमेंट पर कोई फर्क नहीं पड़ेगा. दिस इज कॉल्ड Frank-Condon principle and the transition involved and therefore, it is vertically. Agar if nucleons is moved little bit, it does not matter, like it is an approximation that says the electronic transition most likely to occur without a position change of nucleus, and transition that happens vertically. We are going to anyhow discuss this concept in detail, just I wanted to give you a glimpse and introduction of this. So, in order for a transition from lower state to higher energy state, energy must be provided. So, if suppose we are going from here, because everybody including us, right, want to be on a peaceful state, that is a ground state. If you want to be excited state or if you want to go to excited state, some kind of a stimuli is needed, some kind of perturbation or energy must be given, and that is what we do in the in spectroscopy. So, energy has to be given in order to transition from lower state, that is ground state, to higher energy state. So, energy must be provided, and this energy should come either from thermal energy, right, molecule ke some movement or something, or by absorption of a photon, a light should be shined, electromagnetic wave should be shined, so that it absorbs the energy and goes from ground state to excited state. So, thermal energy can only excite the lower energy state because they are of order of few kBt, and photons are required to take it to the higher energy excited state. The thermal energy, because of molecular motion, it can excite only like a very small energy gap, but this can excite the large energy gap as well. So, electronic and vibrational, like if you look at, if I want to excite from here to here, you require an energy to be given by EM wave. So, here is the ground state and here is excited state, but within the ground state, this is ground electronic state, this is ground. Within the ground electronic state, there are various vibrational state in the excited state there are various vibrational state as well. Now, here when we exploit this vibrational state, that is called vibrational spectroscopy. If I excite from this electronic state to this electronic state, that will be called electronic spectroscopy. If I excite from vibrational state here or here, that is called vibrational state. So, this is done by electronic spectroscopy, this is done by vibrational spectroscopy. So, electronic state is a sum of energy of all electronic orbital, vibrational energy is sum of energy of all nuclear vibration that we see it, right. So, the bold line is basically electronic state and this is vibrational state. So, total energy of a molecule in the ground state will be actually all these ground state, electronic state and vibrational state, and both the electronic state and vibrational state together can be used a technical term called vibronic state. Vibrational plus electronic is vibronic state, right. So, in vibrational spectroscopy, as we discussed or we will be discussing, we will deal with a vibrational spectroscopy in IR. Here electronic spectroscopy, if we excite from here, it goes to here somewhere, that is a electronic spectroscopy, right. So, that is a lower electronic state, this is the lowest vibronic state, vibrational plus electronic, you see this can merge and that will be called vibronic state. So, let us see, as I to sum up what we discussed in this 10 minutes or so. So, what we are saying that there are various energy state, ground state, this is the ground state. Within the ground state there are vibrational state, within the vibrational state there will be rotational state. So, this is the ground electronic state, vibrational state, rotational state and all those. So, the basic concept is all these states are energy quantized, that means molecule can pass from a specific quantized energy level like a steps in the ladder that I gave in the previous class. So, it cannot happen in between, right. It has to go from here to here or here to here or here to whatever various vibrational spectroscopy when we are doing, it will go to here to here, here to here, that is what it is like a climbing a ladder, right. So, for like when we want to go from here to here, I require this much energy or this much leg space to go up. Similarly, from a molecule when it goes from this state to this state, you require an photon energy, right. You, as I said, it cannot be done by thermal energy if the energy gap is too high. Photon energy h mu that should match with the energy gap between these two states. So, delta E is the energy gap between ground state to excited state, should match with something called h mu. H mu is the energy coming from this photon energy, right. So, ground state is the lowest energy, most stable state, electron rest all the time there. The excited state is the higher energy and it because of the ground state electrons are absorbing photon going to this. Degenerate state 2 energy at the same state, right. So, that is what is the difference between ground state, excited state, degeneracy, and it can happen as it happens in all of our life, that we want to be in the equilibrium state at the ground state, but if some energy is given, you are excited by some phenomena, one can go to excited state, but you do not want to be there because that is not a equilibrium state or most peaceful state. So, what do you do? Return back to the ground state, that is called return to ground state. After excitation, molecule can typically come to the ground state, and when it comes, so in the ground state it was the lowest energy, when it went to excited state it absorbs the energy, when it comes to the again ground state, what will you do? Release the energy or transfer the energy. Now, this transfer of energy that is happening when a molecule is coming from the excited state to the ground state, it can emit the light, right. So, there will be light emission releasing energy, it can emit the heat or transfer to some other molecule and that produce the observable signal, right, and that is the observable signal that we detect, right. So, this is the matter where there is a various energy state. इस energy state को we are exciting by providing the photons, right, when it goes from ground state to the excited state. Now, when they come back from the excited state to the ground state, it emits the light, and that light emission or heat emission or a transfer of energy is the quantifiable signal that we observe by detector in the spectroscopy, right, and that gives the property of this molecule. Therefore, to understand the property of this molecule in this phenomena, light matter interaction phenomena, it is important that there is a ground state and excited state, and this molecule can be excited to the excited state by providing a light source, and when they emit it, we observe it and we understand this is the phenomena of the molecule. So, molecule energy level describes the allowed energy, and it is base is the ground state, it transmits the energy. These are quantized gap and we can study in the physics, right. So, that is a main phenomena of a spectroscopy. In all spectroscopy, what we are going to do? We look for this energy gap, ground state, excited state. We shine a light, appropriate light that takes from ground state to excited state, and then when it comes back, it gives you light, right. So, as we discussed, there are various kinds of a state. Electronic state, then in between line is a vibrational state, then the smaller line are rotational state, and that gives to different kind of a spectroscopy. So, electronic state, the energy level is say few electron volt, that gives UV visible lights. So, energy gap is higher, you excite a molecule, highest energy change that happens because of electronic transition, and these electrons basically goes from the ground state to higher energy state. This happens in the region of ultraviolet and visible region, that is a electronic spectroscopy. Then when we excite from one vibrational state to another vibrational state to third vibrational state, this is called vibrational spectroscopy. To excite, if you look at energy level of the electronic state like this, vibrational is like this, rotational is like this. So, here the energy required is less, right. So, this is given by infrared spectroscopy, and the energy scale is 0.1 to 1 electron volt. This comes vibration in the molecule coming because of the bond vibration. So, stretching or bending of chemical bond, and that detected in infrared spectroscopy, right. Infrared camera you have seen, right, this all night camera or CCTV camera are works also in infrared domain. So, energy here required to excite in the molecule is very less, and that happens because of vibrational spectroscopy. Now, you have seen the microwave in the kitchen, right, that hits the water or something like that. So, this microwave energy is even less. So, 10 to the power minus 3 to 10 to the power minus 1 electron volt, this excites basically the rotational levels of the molecules. So, here this excites. So, water molecule can be excited using microwave, and the molecules rotate, right, here rotation is happening and this bond rotation, and you can excite this bond by microwave erosion. So, water molecule typically can be excited by microwave, and that is this phenomena we use in our kitchen for heating water or milk or something like that, right. So, this is the rotational spectroscopy. So, electronic spectroscopy, the color of chlorophyll, right, in plant, because it rises the transition in the electronic level, absorbs light in the visible UV visible region. Then comes vibrational spectroscopy by bond vibration, CO stage or H2O stage or HCl stage, all those are in IR spectroscopy. This gives the identification of the functional group in the chemical moiety. You have seen OH has a different frequency than CO, than CHO, that is a vibrational spectroscopy. And then comes rotational spectroscopy, water vapor in the atmosphere absorbs the microwave, causing rotational transition, and crucial for weather, radar or astrophysics and all those, we can use this rotational spectroscopy. So, in day to day life, we use here in the kitchen for heating the water. In day to day life, we use vibrational spectroscopy for molecular identification. If you want to understand what the chemical or functional group of a chemical molecule is, you can use vibrational spectroscopy, or like understanding anything in UV visible region, we use electronic spectroscopy like a chlorophyll or hemoglobin, red ka color or blood ka color red or green ka color leaf is happening in the electronic spectroscopy, right. So, I am giving an example. These are like here we know that where we are using vibrational spectroscopy. Suppose you are a very exploratory person and you went to a art museum and you want to understand that this painting looks beautiful, but it was painted in 13th century. What color have they used that it is still not like a painting, right. If you go to Ajanta and Ellora cave and you are working in an archaeological department, you will be puzzled to know that what kind of dyes they have used, and you can probably use this vibrational spectroscopy to identify these dyes, and you can, if you are interested in those, you can restore those beautiful paintings. So, that is the use of vibrational spectroscopy in even the history, restoring the history, and rotational, as we discussed, it is crucial for weather, radar or stroke physics, right. So, energy contribution in the molecule, to sum up, we have a electronic orbital, we have a electronic spin, we have a vibrational energy, nuclear spin. The energy typically starts from say 1 to 10 electron volt, this is smaller like a milli electron volt, this is 0.1 to 1 electron volt, and much smaller in like a micro electron volt in nuclear spin. Electronic orbital, its electrons occupied discrete molecular orbital, energy arises from electron interaction with nuclei and each other, solved by Schrodinger wave equation. Then electronic electronic spin are basically electronic angular momentum that we looked at. Vibrational spectroscopy, as we discussed, molecule vibrates, bond stretching, bond bending, this kind of motion that is done. So, it is quantized harmonic oscillator, and nuclear spins, atomic nuclei have a spin creating the magnetic moment, that is done in the NMR spectroscopy, and that is what we study, the nuclear spin. What is the physical origin of electronic orbital? It is a quantum mechanical wave function that describes the electron function, and we use this spectroscopy in UV visible. We can like use this probe to transition happening between ground state to excited state like a hemoglobin or chlorophyll. Electronic spin, we can say spin orbital coupling, and many of the time EPR or ESR is used electronic spins. So, influence the fine structure of a spectra on magnetic resonance. Vibrational spectroscopy, like a functional group identification we do based on the infrared spectroscopy and functional group identification, and this is NMR spectroscopy that we use it. So, these are various kind of spectroscopy that we were discussing, right. So, essentially what we are going to do is essentially we will be diverging into this wave nature of the EM wave, how it propagates and how we can use it to understanding the electronic behavior. But before I give you the details of those, let us see what we measure in the blood, right. So, we know that in blood there is a hemoglobin. So, here is a say hemoglobin. Hemoglobin has a red color, right. We know blood has a red color. So, hemoglobin in blood absorbs a specific wavelength, and that basically pulse oximeter we were using it, right. So, pulse oximeter was giving you some pulse. In pulse oximeter, hemoglobin was absorbing the wave here, light wave, and that we were putting the finger. During COVID, everybody was using pulse oximeter. So, the principle that we were using, differential absorption. Kaise? Like we take oxygen and then our hemoglobin gets oxygenated. So, that absorbs the infrared at 940, and when it gets deoxygenated, hemoglobin absorbs red light at 660. Now, this absorption happening in infrared at 940, and when it leaves the oxygen, it is happening. So, we can take this differential absorption, and that is what pulse oximeter was using, this difference to measure the oxygen saturation level, right. So, you can put your finger, within a minute it was giving how much your blood is oxygenated and deoxygenated. So, that says that what is your value, and that is the basic concept of absorption of infrared light by the component of blood was giving that how much oxygen is going in your blood. So, the concept, simple concept of a spectroscopy now packed in a device used to give a very important phenomena of your life survival, that is oxygen saturation level. Now, what we use? A probe, that is typically your finger, shines both red and infrared, that electromagnetic wave, and a detector that measures the light transmitted. So, more oxygen in the blood means less red light and more infrared light is absorbed. The microprocessor that is packed here was using this ratio of absorbed light to calculate the oxygen saturation level, SpO2 level, and all of us know the clinical application of this. It was non-invasive, just you put a finger here, and that was non-invasive, without taking anything, it was measuring your oxygenated level. So, pulse oximeter, it offers a painless non-invasive method for continuous monitoring of patient blood oxygen level. So, it says critical parameter like oxygen is very critical for anybody's survival, and if it goes down, one has to put in on oxygen. So, this is the simple non-invasive method based on the concept of spectroscopy, differential spectroscopy is giving a vital survival parameter. So, it is a vital tool for assessing respiratory health in various medical settings, and this demonstrates how electromagnetic wave and this sample, that is matter interaction, can be applied to create a life saving medical technology, right. So, the concept of spectroscopy in biology, because it is measuring the hemoglobin, the absorption, used in life science by this pulse oximeter to make a simple device that is so critical for anybody's survival. So, that is what I want to end it here today by saying that concept of a spectroscopy is extremely simple and very applicable to life science, and that is one of the classic example of pulse oximeter. I hope you appreciate the concept, and but it does not only spectroscopy, miniaturizing this, you have to have a sensor, you have to have infrared light and process this in display. So, lots of engineering concept has to be integrated in the concept of a spectroscopy to make this wonderful device that everybody now has in their home, right. So, thank you very much, and I hope this will excite you why you have to understand a spectroscopy in detail. I gave you lots of example from the daily life by just heating the milk or water, by microwave, then identification of a functional group. In chemical moiety, you can look at you can differentiate between aldehyde and alcohol or carboxylic acid, that is by IR spectroscopy. The chlorophyll green color or the red color in hemoglobin by UV visible spectroscopy, and nuclear spins or electronic spins in ESR and NMR can be studied. So, I am going to stop it here and look forward to see you in the next class. Thank you very much.